Okay, so in chapter 5, we did a whole bunch of things on forces. We started explaining what is a force, how do things move. We did in chapters 3 and 4. In chapter 5, we tried to explain why does it move. Now, we did quite a bit in chapter 5. Honestly speaking, chapter 5 was not a light chapter. There was quite a bit on it. Newton's first law, second law, third law, common forces, and quite a bit. And it was very light on examples. We did very few examples. So what's going to happen is actually chapter 6 is going to be bucket loads of examples on what we did on chapter 5. And let's start. Okay. All right. So I'll do something here. Right. So share screen, share. Yes, midterm will be online. Yes, we will have a quiz next week. More Q&As after we finish the lecture towards the end. Okay. So this is the last thing we did in the previous lecture. We introduced tension, and then we did one example of a block being pulled on a ramp. Okay, now moving on. Normal force on box on an inclined plane. So we will be trying to include extra forces and projections. So let's consider 3 cases without numbers first, just to get a feel for it. We will consider 3 cases shown in these drawings. The same force F is applied to the same box of mass m. In which case will the magnitude of the normal force on the box be equal to F sine theta plus mg? Okay, so most people are between A, C, and oh no, we have D's, we have E's, we have C's as well. Okay, let's take a look. We define the normal force to be the force that is upwards, right? That is balancing the forces that are going downwards. Here they say F sine theta plus mg. Fine. Here, in case 1, our mg is going to be down like this, right? So there's an angle on it. So it is impossible for us to only have mg. We will have mg with sine, with cosine, with some angle component. So we know that case 1, this is not possible. So this cannot be. Anything with case 1 in it cannot be possible. We are left with B, C, and E. Case 2, case 3, and cases 2 and 3. Okay. let's take a look at case 2. What are the forces here? We have mg down, we have the normal force up, and we have this force at an angle, right? Now, if we try to balance these forces, what we end up with is, first, let us break it down into components. F will have a component like this and a component like this, which means since my block is not floating, the sum of these will need to be 0. So n plus f sine theta will be equal to mg. N equals mg minus f sine theta, and this is plus. So case 2 is also wrong. So anything that involves case 2 is also wrong, which means the only case where this is correct is case 3, C. We do this quite a bit, at least I do. Okay, because I'm very fat.
Doctor, please,
Yes.
can you repeat the last question? I didn't get it.
Which last question? This one, the one we're just doing now?
Yeah.
Sure. Let me first just double check something. Okay. Why is this thing? Okay. We have a block, right, of mass m. It is being pushed or pulled in this direction, F with some angle theta. Okay. Now, what do we know for a fact? We know it moves in x-axis. We know it does not change in y-axis. Are we okay so far?
Yes.
Okay, so far so good. We know that in the y-axis it is fixed. It does not float up. It does not go below the table. It is just there. Now, from Newton's second law, we know that the sum of forces is equal to ma, right? Now, if it is not changing in the y-axis, okay, it means if it is not changing in the y-axis, okay, it means that the sum of the forces need to be equal to 0. So we start by drawing all the forces on our block. We know it experiences gravity downwards, and it experiences normal force upwards. Okay. We also know it experiences this force at some angle theta. Correct? So we have hypotenuse, opposite, adjacent. And I am going to break it down into components. Since it's going up in this direction, its components would be partially in this direction and partially in this direction. Yes? In the up direction, yes, it will be F sine theta, because sine is opposite over hypotenuse. And in the x-axis, it will be F cosine theta. Now, on the x-axis, we already agree that it's moving, but we know that it's not moving in the y-axis, which tells us, because it's not moving in the y-axis, it tells us that the sum of the forces, which is mg minus n, because it's in the opposite direction, minus f sine theta is equal to 0. Now, the question wants us to find what is the normal force. Okay, so I'll just rearrange. I will take n to the other side. So this will give me n equals mg minus f sine theta. Okay, and this is not what the question wants. The question wanted f sine theta plus mg. So we know it's not this case. If we do the exact same thing, but with the force going downwards, we will end up with a plus here.
Thank you, Doctor.
No worries. Okay. I have minus because it's in the opposite direction. The directions are opposite. Remember, forces are vectors, so directions are very, very important. Okay. Azan, if you want the normal to be positive, then your mg will be negative. It's not an issue. So if I want my normal to be positive, that's fine. I will do n plus f sine theta minus mg equals 0. So my n will still be mg minus f sine theta. Okay, so you will end up with this and this being absolutely equal. All right. Now this is something that we do on a regular basis. Check what our weight is. Okay. What we're doing is we are measuring Fg. I have a certain mass, okay, 50 kilos, 80 kilos, 100 kilos. And that means gravity is pulling at me with an F gravity, which is ma, which is mg, which means m's times 9.81 meters per second squared. Now, because I'm not going through the scale, it means the scale is also pushing me back up, okay, with a normal force, Fm. Okay, this is a very, very heavy child. Okay, so how does this work? Let's consider the case of a man on a scale on an elevator. Okay, why is it not changing? Okay, this is frozen. Give me a second. Okay, hopefully it goes back now, works. Ah, there we go. Okay. So let's consider what happens here. All right. A man standing in an elevator, and the elevator is accelerating upward with some acceleration A. What is the reading on the scale? Will the reading on the scale be MA plus MG, MA minus MG, MA, MG, or just 0? Okay. First thing first, we need to draw a free body diagram, always in any problem involving forces. So here's my man, very, very big dot. There's the force of gravity downwards. There's the normal force upwards. Since the elevator is accelerating upwards, it means there is an extra force, MA, going up. Okay. Any other forces? No. Now, since our previous slide told us that what the this thing is deciding not to work. That what the scale is showing us is actually Fn. What we need to find is, what is Fn? The person is not floating. The person is not accelerating. He's still in the lift, no problem. So the sum of the forces is equal to 0. So do you want mg to be, or do you want positive to be down or up? I'll choose mg down to be positive, okay? So mg minus n minus ma equals 0. Okay. Which means that n equals mg minus ma. So the reading on the scale will be, ooh, interesting, none of them here. Let me try the other way around. Take up to be positive. So I'll do n plus ma minus mg equals to 0. Which means n is equal to mg minus ma. Interesting. Very interesting. Why are none of my options correct? I might have made a mistake. تراهم نفس المعادلتين. That's the exact idea. And it doesn't matter whether you take mg down to be positive or up to be positive. This is the whole point of it. Okay. But the question is, why are none of my answers correct?
Doctor, in equation number one minus n minus mg. In equation number 2, you shifted only the same equation.
It's the same equation because it's the same variables. Our variables here are the same. The only thing is, in the first equation, in the first time, I took mg down to be positive, and the second time I took up to be positive. So let me take a look. Well, let's see. I will take everything I wrote, and I'll bring it all the way over here. And let's see. So we have our passenger, our force of gravity is down, and our Fn is up.
دكتور الآن it is positives because it's up لكن الام جي ناخذها عندنا يعني تحت ماينس اور فوق ماينس كيفنا بس الان لازم موجب.
ليش لازم موجب؟
الجي فقط تختلف إن إذا تحت acceleration سالب أو فوق سالب.
لا كل القوى كذلك. All forces. All forces are like this. It's all about the direction. If you choose one direction, you have to stick to it. Okay? So if I choose this to be positive, then this is positive. It needs to be negative because it's in the opposite direction. Yes?
ما المفروض لأن اللي هي قوة الاحتكاك ما المفروض تكون عكس اتجاه الحركة؟
ما شرط تكون عكس اتجاه الحركة. N is not قوة الاحتكاك. N is not friction. We haven't spoken about friction yet. This is the normal force. This is not friction force. We haven't spoken about friction at all. Okay. So no one knows where I messed up? No? Okay.
دكتور أنا لما جلست أفكر الحين إنه أوكي الأكسلريشن بناخذها على إنه فوق والإم جي دامها هي أوريدي تحت فناخذها على أساس هي بلس تحت بتكون ماينس لما هي بتكون فوق. تكون الجواب يكون الجواب A.
Why?
دكتور الحين ما لما الاليفيتر يتحرك على فوق بيدفع الجسم على تحت.
Okay, yes.
فبتكون جمع اللي هو وزنه اللي هي ام جي بلس قوة الدفع اللي عليه تحت.
Excellent. Who is this, by the way? I can't see names.
أسمع.
Your point is exactly correct. Okay. Nope. ما غلطان في الإشارات. You're absolutely correct. I chose the wrong system. Okay. Remember in the previous lecture when we were talking about systems. Okay. And we said we need to decide what is our system of operation, and internal forces don't count on the system and external forces count. Now, the choice of system is a rather important thing to do. Okay. If I choose the wrong system, I end up with the wrong solution. What I did was, okay, so to start from scratch, if you haven't been attention so far, please start paying attention now. Okay. The mistake I did was I chose to look at the forces on the lift, not on the person, which gave me the wrong directions, which gave me the wrong final answer. Okay. As your colleague just said, I should not be looking at the lift because what I'm looking for is the reading on the scale, but not of the lift, but of the person. Okay. So if now I do it properly, I look at the person. Okay. I have mg down. Yeah. I have my normal force up. And as the lift is going up, okay, it is going to push the person down. So I will have one more force, MA, down. And now I will take mg plus MA minus N is equal to 0, mg plus MA is equal to N, and I get this to be my correct answer. Okay. Now this is very, very important. The mistake I made, okay, was a mistake that is easy for any of us to do. Okay, choosing the wrong system. What I did wrong, I'm going to say it one last time so that you get it. I drew the free body diagram of the forces on the lift instead of drawing the free body diagram of the forces on the person. So I ended up with a wrong final answer. Okay. Let's look at B. Another man stands on the scale inside an elevator that indicates his weight is W when it is at rest. So when the lift is not moving, it will give the weight W, whatever W is, 10 kilos, 10 newtons, something. What will the scale read when the elevator is moving upward at a constant velocity V? Look at this word. It's very important. Constant velocity. Okay, you are correct. You are correct. The answer is C, but some of you gave a wrong reason why the answer is C. Yes, W equals N, but that is only when, so this is what W is, right? But that is only when it is at rest. Now, the key point here is, because acceleration is 0, the second term will remain 0. So as long as the lift is moving at a constant speed, constant velocity, there is no acceleration, mg is equal to n, so the scale will still read the same value w. If it was accelerating, we would be reading a larger value. Okay. Think of it, if you have ever gone to a really, really fast lift, as soon as the lift starts moving, you feel as if someone is pulling you downwards. Okay. Let's do another example. A 40-kilogram skier skis directly down a frictionless slope angled at 10 degrees to the horizontal. Assume the skier moves in the negative direction of an x-axis along the slope. A wind force with component Fx acts on the skier. What is the Fx if magnitude of the skier's velocity is constant, increasing, or increasing at an even different rate? This is a normal problem. Okay, so what I'm going to be doing is, I will not be doing it on the slide. I will go to a whiteboard and we will do it together. Okay. A bit bigger. Okay. So, frictionless slope angled at 10 degrees to the horizontal. Very exaggerated diagram, but this is 10 degrees. We have a skier skiing down. Mass is equal to 40 kilograms. And it wants us to assume that the skier moves in the negative direction of an x-axis along the slope. Okay, so they want us to draw it in a very, very specific way. They want us to draw it this way. Okay, and they want us to define the x-axis and the y-axis to be like this, and the skier is moving in the negative direction. A wind force with a component Fx acts on the skier. So we have wind force. What is Fx if the magnitude of the skier's velocity is constant, increasing, or increasing at a different rate? So what I drew now, this is not a free body diagram. This is just a photo. Now let's do a free body diagram. This is my person. How should I draw this? Let me draw a hybrid diagram, because that would be easier. Okay, I will have my person like this. I will have mg down, normal force up. There is no friction. Okay, and there is a wind, which is Fx, but we don't know if it's plus Fx or minus Fx. Okay, so how do we do this? Let's resolve the components. There will be one like this and one like this. Which one is cosine? Which one is sine? Can anyone help me?
Add the down sign and here cosine.
Okay, everyone agrees? Anyone disagrees with this? Okay. I have no idea. I'm going to do it with you right now. Let's take let's leave this in our mind. You calculated to be 386.4 newtons for first. So let's try it out. So remember, x and y axes don't speak to each other. They are upset with each other. So in the y axis, yes?
Why you write cosine up and sine down?
Your colleague told me this is the right one and no one disagreed. Do you disagree? Do you think it should be cosine down and sine up?
No. Sine up, cosine down.
Okay, so you think it should be the other way around?
ايوه صح دكتور، العكس.
قبل شوية يوم سألت في حد disagrees، ما حد قال لي. Let's see.
دكتور ترى شوف الزاوية لا غير شوية.
Okay, let's do it together. Let's do it together and see which one is sine. Which one is cosine? We have this to be 10 degrees. We are doing this. This is 90 degrees. Okay. This is also 10 degrees.
دكتور يعتمد على حسب الزاوية هي تاخذ هي.
صحيح.
إذا خذت الزاوية بين الام جي هذه المحور اللي تحت الواي تكون بدل الساين كوساين.
So this is all we know. We know this is 10 degrees. We know this is 90 degrees. So this has to be how many degrees? Okay, so I do 10 plus 90 minus 180. So this has to be 80 degrees. صحيح. This is 80 degrees. This shows us it is very important to draw it. Okay, I honestly don't know if it's sine or cosine because there is no hard and fast rule. It really depends on the angles. So the only way for us to actually figure out which one is sine and which one is cosine is to actually try it out. Okay, so let's try it out. This is 80 degrees. This is 90. This is 10. So cosine down and sine up.
ايوه كي صح دكتور.
We agree on this?
ايوه.
Okay, let's see if it works out. Why do we have people joining the lecture at the last moment? Or is my phone going crazy? You should not have a mid during another lecture. You should not be, this is a university rule. No mids in the middle of other lectures. This is not allowed. Okay, can you do me a favor? Anyone who just joined or anyone who joined late because they have another mid during this lecture time, during a scheduled lecture, please email me and let me know what course did you have a mid in and from what time until what time, because these are very clear instructions. No midterms should be during another lecture's time. Okay. I'll be expecting at least 10 emails, give or take. Okay. All right. So in the y-axis, we know. تو الحين اللي جو متأخر الحين 3/4 الليكتشر راح عنهم. من يشرح بعدين؟ اللهم طولك يا روح. Anyway, okay. So in the y-axis, we know mg cosine theta is equal to n. In the x-axis, we have three cases. We have case A, velocity equals constant, meaning acceleration is equal to 0. We have case B, acceleration is equal to 1 meters per second square. And we have case C, 2 meters per second square. Now we know there is a wind force in the x-axis. We just don't know whether it is going up or going down, or what its magnitude is. And what it wants is to find what is the magnitude of the wind force. Fine. So let's do A. Sum of the forces is equal to MA, which means that mg sine theta plus the force of the wind need to be equal to 0 because our A is 0, which means that my force of the wind needs to be equal to minus mg sine theta. We only want the magnitude, so it will be 40 times 9.81 times sine 10, which is 68 newtons, give or take.
دكتور ما فهمت نقطة إنه y in the x-axis there is a 3 cases y axis ما في case. على أي أساس خذينا؟
Because our skier is going down the slope. Okay, he's not going up or not going down, صح? So the sum of the forces in the y-axis is equal to 0. The question is only asking us about the x-axis because the wind is only in the x-axis. This is how the question is formulated. Okay. Case B, sum of F equals MA equals 1 meters per second, which means that F wind should be equal to minus mg sine theta plus 1 meters per second squared. Yes, I'm not messing up, am I? Minus mg, and it should be 1 on the other side. So it should be giving us 67 newtons. And C, using the exact same thing, it should be giving us actually no. No, I made a mistake. The first case is correct. The second case, sum of F is equal to MA. So mg sine theta plus FW is equal to MA, so 40 times 1. Which means my wind is going to be 28 newtons. So 68 minus 40. Okay. So here, without magnitude, it's going to be minus 68 newtons. Here it's going to be minus 28 newtons. And for case C, doing the exact same thing, I will get minus 11 point something, minus 12. So minus 11.9. So I'll say approximately minus 12 newtons. No, not minus. Should be plus, not minus. Plus 12 newtons. And if I take only the absolute values, then I will get magnitudes of 68 newtons, 28 newtons, and 12 newtons. أيوة.
Same if you write mg sine theta minus fw.
No, I want to find what is FW. So FW is equal to MA minus mg sine theta. So we know that mg sine theta plus FW is equal to MA. I want to find FW.
Fw is equal mg sine theta minus ma.
Like this. Yes?
Yes.
We keep FW. So MA minus mg sine theta. Yeah?
ma not equal mg sine theta minus fw.
No, why minus FW?
ma equal mg sine theta minus fw.
Why minus FW? Why not plus FW? Remember, we don't know the direction of FW, yeah? If it's up or down.
I think it's minus because up.
How do you know?
قوة الرياح.
But how do you know? But how do you know it's up? We don't know if it's up or down. Remember, the question only tells us a wind force with component Fx acts on skier. It's not telling us if it's Fx is positive or negative. So we don't know if it's actually going up or going down. If it was going up, you would be correct. But we don't know if it's going up or down. So we simply literally go sum of F, which means Fg plus Fw. Now, if like in these cases, see, in two cases, this one and this one, we got Fw to be minus. This tells us that's in the opposite direction, in the up direction. In the third one, okay, however, we got it to be positive 12, which means the wind is in the direction of the movement, going down, not up.
I thought the same you, but that you write it minus, I write it يعني لأني بس التغيير عندي في الإشارة.
أيوه لأنه you assumed أنه the wind is going up, but the question did not tell us it's going up. So we leave it general and we see what the result tells us. Okay. So Mariam, when اتجاه FW at the beginning of the question, we don't know. Okay. At the end of the question, we know in case 1 and in case 2, wind is going up. In case 3, wind is coming down. Okay. Let's do a few more examples, a few more things. صينيين لعوزون لعوز الله بليسم. Okay. So some of you were already invoking friction. So let's actually speak about friction. Now, friction always opposes the motion which would occur in its absence. What does this mean? And friction is always parallel to the surface. What does this mean? Okay, it means that, say, I want to go in this direction. Friction is a pain, so it would act exactly in the opposite direction. Okay, it wants to stop whatever I am doing. If I am going in this direction, then it will act in this direction. If I'm going in that direction, it's going to act in this direction. If I'm going left, it's going to act right. If I'm going right, it's going to act left. Okay, it only has one purpose in life, which is to make our life complicated. Okay, it wants to stop motion. Okay, so if I have a block which is going to the left, okay, it's going. If the block is going right, the friction is acting left. So this should be 6.2. Okay. What causes friction? If we zoom in into anything that we have whatsoever, okay, we have a very bumpy picture of the world. So it doesn't matter how nice and shiny something is, how smooth it feels. When we zoom in to the using a very nice microscope, we would end up seeing a rather bumpy ride. Okay. Now, friction occurs because these bumpy things slide against each other. So like we're used with rough surfaces on a macro scale, but this happens all the time at the microscopic scale. Okay. Now, what happens is, you can reduce friction by making it smoother and smoother and smoother at a microscopic scale. Okay, and you can make it so well, you can make it so smooth that at the end of the day, okay, at the end of the day, you can have two specially prepared metal surfaces that simply cold weld, so that you don't have enough friction. When they come together, there's not enough bumpiness. The microscopic forces, the attraction forces microscopically, okay, will cause them to stick to each other and weld. Okay, so believe it or not, if we have very, very low friction, generally speaking, that might be a bad idea for things in general. I wouldn't want my hand to stick to this pen. Okay. All right. So we have two objects. One is of a granite and another is a piece of wood. Okay. See, the interesting thing is, while I am trying to explain things, some of you are busy typing and chatting. And in about 3 or 4 minutes time, you are going to ask me about the exact same things that I just spoke about. Okay. And then you're going to be upset if I tell you I just explained that and I'm not going to re-explain it because you were busy chatting. Okay. So it really doesn't make a difference to me. You can type all you want. If you think, okay, I'm not going to type here, I'm going to type on a WhatsApp group, I'm going to do it somewhere else, it really doesn't make a difference to me. It is you that is suffering. Okay, so how do we know which one has more frictional force? Frictional force, okay, there's a way to quantify it, but on a very, very basic scale, okay, we say frictional force is always proportional. This sign means proportional, okay? Frictional force is proportional to the normal force, okay? So whatever the normal force is, okay, our frictional force is going to be directly proportional to that. Okay. So, the question is, okay, why is it proportional to the normal force, not the gravitational force? Since, you know, we said that if something is on a surface, then Fg is equal to Fn. Yeah? Why is it different?
Maybe because it is opposite direction.
Okay, but the magnitude is different, the same, right? So if the magnitude is the same, then the proportionality shouldn't matter. Yes, the direction would matter, but the proportionality constant wouldn't make a difference. We can just add a minus sign. Why don't we just depend on Fg? Why on Fn? Well, that is all fine and correct up until I start acting on a force. Now, if I have my calculator here and it's resting on my hand, and I am not sure if this is showing in the photo or not. Okay. Okay. Now Fn equals Fg, right? What about now when I'm pushing on it? Fn is no longer to Fg. Fn now is equal to Fg plus F applied, right? So Fn is different. Now, if I try to move this, the friction isn't going to be because of gravity, because gravity is push. Okay, pull downwards. It's going to be proportional to both the gravity, the sum of gravity and the pushing that I am doing. So, in the absence of an applied force, Fn equals Fg. But as soon as I apply some form of force, we will end up with Fg plus F applied. That is why friction is always proportional to normal force. Okay? And it works the other way around too. Sometimes if you are trying to pull a very heavy push or pull a very heavy box, it will be very difficult, but you'll ask a friend of yours, okay, just slightly raise it up, okay, and I'm going to push it, and it makes things easier. Why? Because if I do that, then my force diagram is going to be Fg, but I will have Fn and Fap, which means my Fn is going to be Fg minus Fap, making the friction lower. Okay, Fn is normal force. Okay, so Fn is F normal. Okay, so how do we increase the frictional force? Let's see if we have understood this. A block slides on a horizontal surface. Which of the following will increase the frictional force on it? Putting a second block on top, decreasing the surface area of contact, increasing the surface area of contact, decreasing the mass of the block, or all of the above? Remember, we want to make the friction force more. Okay, we have answers all over the place between A, B, and C. So we all agree this is not possible, and we all agree this is not possible. So we said friction is proportional to Fn, right? And we said Fn equals mg plus whatever force we are extra applied. Area does not actually factor into this. Okay, which means increasing the surface area or decreasing the surface area according to this equation does not really make a difference. The only one would be is putting a second block on top, because then your Fn would become mg plus mg of block 2. Yeah. Okay. Here's a very big shopping cart, really, really big. And we have an elephant in it. And I'm pushing it with a force F. Okay, here is me trying to push the cart with the elephant, and nothing happens. Okay, and I get one of you to help me. Still nothing happens. I get one more of you to help me. Still nothing happens. And finally, when we have 4 people helping me, oh, it started moving. Okay. We don't need a 5th person. It starts moving. So there's a threshold. This teaches us that there's a threshold after which it starts moving. And we knew this naturally. If I'm trying to move this and I'm just trying to do it just nicely, it's not going to move. I need to push it with enough force to move it. But how do we quantify this in numbers? So F here is the applied force, and the blue one here is the friction force. Okay. So as long as the friction force is equal to the applied force, there will be no movement. The only time when there is movement is when the friction force is less than the applied force. Now, this is what happens. Initially, when we're pushing, there's no movement, no movement, no movement, no movement. And once it starts moving, then we have this. Now there's something funny here. Okay, it started moving here, but why does it go down? Okay, why does it go down? Why doesn't it just stay where it is? We'll come back to this in a bit. Okay. Yes. A block lies on a floor. What is the magnitude if the frictional force on it? What? Not if. Of. It's supposed to be of. It's not working. I can't fix it. Okay. A block lies on a floor. What is the magnitude of the frictional force on it from the floor? 0, 5 newtons, or mg? Okay. Okay. So some say 0, some say mg. Okay, let's go to the next question, then come back. If a horizontal force of 5 newtons is now applied, but the block still does not move, now what is the magnitude of the frictional force? And you have the exact same 3 options. Okay, here's a question. What did we define friction to be? No, we did not define it to be mg. I'll go back to the slide. Very first slide. I said 6-2. What's wrong with you? We said friction always opposes motion, right? If there is if we're not trying to move it, then there is no friction. Okay, it only works if we're trying to physically move it. Okay, look here at the beginning, when we're not trying to move the elephant, what is the friction? 0. I'm not trying to move it, so there is no friction. It's happy as it is. Only when I start trying to move it and I apply a force, do I get an equal friction. I increase the force, I get an equal increase in friction, and so on and so forth. Okay, so when it's just lying on the floor, I'm not even trying to move it, there's no friction. I'm not trying to move it, it's not opposing my motion. Yes, when I am applying 5 newtons and it's still not moving, its friction is exactly 5 newtons. Why do you insist it's 6-1? Okay. Now there are 2 types of friction. We're going to introduce it, and then we're going to end today, and tomorrow, inshallah, and next week, inshallah, we're going to explain, to do examples and continue forward with it. Okay. We have 2 types of friction. One is called static friction, when things are not moving, and one is called kinetic friction, when things are actually moving. What's the difference between them? Remember that diagram I told you we'll come back to? Well, we're back. When we are not moving, okay, when an object is just here, it has enough time for those bumpy microscopic things to get attached to each other. Okay, so its friction is actually slightly more than when it's moving. Okay, because when it is moving, those forces are constantly creating bonds and breaking them, creating and breaking them while you're moving. Which means that if I am trying to move something that is not moving, I actually need, okay, to increase the pressure, the force I am putting on it. Okay, so Fs max is equal to mu s Fn, where mu s is called the coefficient of static friction, and this is not a vector relation, it's just a number. Okay, so if I want to find the friction force when something is not moving, and yes, Bushra, we can speak about it when I'm done with the lecture. Okay, so we multiply the normal force by mu s. Now, the value of this coefficient of static friction depends on materials in contact and is usually less than 1, but I am going to add it here in red, but can what's wrong with this? Be more than 1 in some cases. Okay, so it doesn't mean, okay, it doesn't mean that cannot be more than 1. It's usually less than 1, but it can go more than 1. Kinetic friction, okay, we have the exact same thing if you want to calculate the friction force of something that is already moving, but now we do mu k instead of mu s. Okay, and it is in this bit. So if you need for example, if you need 100 newtons to move something, okay, to start moving it, it's not moving, it's just stuck, and you need 100 newtons to move it. Once it starts moving, you can go less. Okay, and will continue moving. If you stay at 100 newtons, your speed will actually increase because you are giving it more force than needed to barely move it. So you cause acceleration. And this is always true, pretty much, almost. Okay, there are very few exceptions to this. Mu k is less than mu s. Okay. Actually, I'm going to say there are no exceptions to this. Mu k is always less than mu s. Okay. I think this is enough for today. We can... Yes, this is enough for today. We can continue the rest in the next lecture. We've already gone 3 minutes over time. Okay, thank you for attending, and see you all in the next lab, tutorial, lecture, whatever it is. Someone wants to speak to me, Bushra? Just give me a minute.
Okay.
I'll stop recording.